Okay, we want to use Lagrange multipliers to find the extreme values of f of x, y, z equals 2x plus y plus z. I suppose this is a linear equation, right? But it doesn't graph, it's a hyperplane, I suppose, right? Because it has 3 input variables and 1 output variable, 4 variables altogether. So f is not a plane, it's a hyperplane. And then it has 2 constraints. We'll call the first constraint x plus y minus z. Let's go ahead and subtract the 2, set that equal to 0, and we'll call that g. That's g of x, y, z, right? And that would graph to be a surface in space because it's set equal to 0. And for this one, let's subtract the 5. X squared plus z squared equals, or minus 5 rather, equals 0. So that would be a cylinder, a cylindrical surface, right? Because it's set equal to 0. But we think of h as a 3-input function and then set equal to 0. And so the idea is x, y, and z has to be on the intersection. It would be a curve because both of these are surfaces. X, y, and z would have to be on the intersection curve of g and h for it to be in the domain of f. For you to be allowed to plug it into f, it has to be on both surfaces g and h, which means it's on the intersection curve. All right, well, what does Lagrange multipliers say? Del f is equal to lambda del g plus, we have to use another letter here. Mu, right? That's another Greek letter, mu del h. Remember that? Okay. So what does this mean then? It means we've got to find these gradients and plug in appropriately, right? Well, let's start with del f. That's easy enough. What's del f equal to? 2i plus j plus k. And then del g. What's del g? Just going to be, I plus I minus k. I plus j, rather, minus k. Right? I mean, I could have looked at this one in orange, I guess. And then what's del h going to be? 2xi. So I'm looking at this guy. 0j, we don't usually put that. You can if you want. If you want like a placeholder, that'll work. And then plus 2zk. And then we've got to multiply through by, del g by lambda. So we just need a lambda in front of each of these. And then del h by mu. So I'm going to put my mu there. I don't really care about that one because it's 0 and a mu there. Okay, does all that make sense to you? All right, so, yes. I'm sorry? Del h. So remember what del h is. It's going to be, if I use, maybe you like component form better. It's a vector, right? So it's going to be h sub x is the first component. H sub y is the second. H sub z is the third. So h sub x there's where the 2x comes from. H sub y is 0. The partial of h with respect to z is 2z. And then I multiply through by mu. Everybody with me? Okay, let's set up our system of equations. So for the I components, I know, okay, what do I know? I know 2 is equal to lambda plus 2 mu x. Does everybody buy that? Okay, so 2 is equal to, what did I say, lambda plus 2 times mu times x. Okay, and then the next one, 1 is going to equal what? Lambda plus, that's it. So we know what lambda equals. That's nice. And then what's the next one? 1 is equal to, so negative lambda plus 2 mu z. Make sure I got that right. 1 is equal to this guy plus this guy, right? Okay, then we have the two constraint equations. I'm going to write the original form. X plus y minus z equals 2, and x squared plus z squared equals 5. We can make these guys a lot easier on the eyes, right? So what happens, let's work through this. What happens if I plug in 1 for lambda and then maybe subtract it? What do I get? I get 1 equals 2 mu x. Okay, that's for the first equation. What do I get if I put the 1 here? And so that's minus 1, right? And then I add it to both sides. What do I get? 2 equals 2 mu z, which would be the same as 1 equals mu z. Does everybody believe that? It's dangerous when you skip steps. It's easy to make a mistake. But yeah, this would be, when you plug it in here, you got the negative in front. Negative this side, add it, you get 2. 2 equals 2 mu z. Divide out the 2's, you get 1 equals mu z. And then these two equations don't change. X plus y minus z equals 2. And x squared plus z squared equals 5. Okay, so we've narrowed it down a little bit. And I'm thinking, okay, I'm going to use the last two equations eventually, right? But I think I can maybe use the first two equations to express z in terms of x, right? Or x in terms of z, or mu in terms of both of them, depending on what we want to do. So what would you like to do here?
Could you set them equal to?
Okay, and then what don't you want to do? Don't divide. Okay, we don't know. Well, I mean, I didn't look at the original function. Do we know that they're non-zero? I don't think so. So don't divide out the x or the z or the mu. Remember the technique. If you don't know that they're non-zero, don't divide by an unknown. That's the general rule of thumb. Okay. So what can you do? Set it equal to 0 and factor. So what? 2 mu x minus mu z equals 0. And then what factors out? Mu. It's a sound either a sick cow would make or maybe a sick cat. I'm not sure. Mew. It's like a cross between a meow and a moo, right? So mu, and then what's left? 2x minus z. So we've got two cases. We've broken this down to two cases. Hooray! Either what? Either mu equals 0 or wouldn't it be easier to say z equals 2x? Okay. There we go. 2x equals z. Same thing, right? Okay. Everybody with me? It's like we're arguing, we're splitting hairs, right? So, if mu equals 0, what happens if mu equals 0? So, let's see. We get an inconsistent statement. Does everybody see why? If mu equals 0, then this whole thing zeroes out. We get lambda equals 2, but we already know that lambda equals 1. That's a contradiction, so we're not going to consider it. Okay? So this is a contradiction. And I'll just point at why. So because if we look at this equation, we get lambda equals 2, but we already know lambda equals 1. So just look at those two equations. You can convince yourself of that. So we know that z equals 2x. That's beautiful news. Why? Not, depends on what you mean by this. How about the last equation? Yeah, because that involves x's and z's, right? So I think the natural thing to do is to replace z with 2x. So we'll do that. And we get x squared plus what? 4x squared equals 5, which means 5x squared equals 5. X squared equal, yeah, 1, or x equals plus or minus 1. Well, all right, if x equals plus or minus 1, what does z equal? So you have to be careful with the order here. So if x equals -1, then certainly z equals -2, right? You can't mix and match here. And if x equals +1, certainly z equals +2. So these are two different lines to follow, and that you can't mix and match the negatives there. And then what else do we need? We need y, right, to get our critical points. So let's use finally this equation right here, x plus y minus z equals 2. X plus y minus z equals 2 is what we're using. So we're just going to plug into here to get our critical points. So if x is -1 and z is -2, that makes a +2 right there, doesn't it? And that means y is equal to what? 1. Because these 2's cancel, add the 1. So what's the critical point there? -1, 1, and -2. Does everybody believe that? Okay, now plug in x equals 1, z equals 2. What do we get? 1 plus y minus 2 equals 2. So that means 4 minus 1 is 3. Y equals 3. So what's the point there then? 1, 3, 2. So I'm only getting 2 critical points. And then what's the last step? Plug it in, plug it in. What was the function? I forgot. 2x plus y plus z. Okay. So where were we? Oh, so we're going to plug I'm not even going to make a table here. There's only 2 points to consider. So not that stopped me before, but I'm just going to plug them in. Okay, so what do we get? -2 plus 1 minus 2. What is that? -3. That's probably a min, right? And then f of 1, 3, 2. So that's going to be 2 plus 3 plus 2 is 7. So I'm going to say that's our max, absolute, and that's our min, absolute.